Hey, in this video you can learn about infinity categories. This is part of a series of lectures we're doing on stable infinity categories and higher algebra. And it's intended so it can be watched somehow independently of the rest of our course on topological cyclic homology. Infinity categories, as pioneered by Joyal, Lurie, and others, are somehow a generalization of both categories and the homotopy theory of spaces. And they turn out to be somehow a natural home for all kinds of derived phenomena. So in this video, we will be talking about some of the basic notions and the infinity category of spaces. We will give a very rough overview and omit basically all of the proofs, some of which are very hard. So we encourage you to check out some of the very good literature on the subject, which we will be linking down in the description of the video. I'm Achim Krause from Mathematics Münster. Before we can discuss categories, we have to mention size issues, which is that if you want to consider, for example, the category of all sets, the collection of objects can't itself be a set, because this leads to usual paradoxes like Russell's paradox. So there are multiple different solutions out of that. The one we will go with here is so-called Grothendieck universes. So what we will do is we will assume a Grothendieck universe U, and Grothendieck universe simply means that this is a set whose subsets or whose elements themselves form a model of set FC. So they're closed under everything you can do to sets, products, power sets, and so on. And we will basically study objects in this universe. So we will call elements of U simply small sets. And analogously, you can, in terms of small sets, define stuff like small topological spaces, small Kahn complexes, all of that. And this has the advantage that now the set of all small sets is itself a set, right? It's not itself small, so we will call sets in general, if they're not necessarily small, large sets. And so if you take the collection of all small things, typically you leave this universe, but you're still in the world of sets. And so for us, categories will typically have large object sets and also potentially large morphism sets. This is a little different from the classical definition of categories, where one requires the morphism sets to be small in some sense. But this is basically another partial solution to these size issues which come up, and it doesn't solve all of these things. It turns out that if you're willing to assume existence of universes, then you don't get much benefit from thinking about small, locally small categories. And for example, when we now write something like set, we mean the category of small sets. Think of this just as a convenient way to discuss away these size issues. Yeah, there's other solutions, but this is one of the more convenient ones. All right, so we now can define what an infinity category is. And infinity categories are special kinds of simplicial sets. An infinity category is a large simplicial set C with the property that any diagram like this, where this is the standard n simplex, this is the I horn, the ni horn. This means that this consists of all the faces of the n simplex except for the ith one, the one opposite to the ith vertex. Any such diagram for I strictly between 0 and n admits such a dashed arrow. So we will think of this as a map filling the given horn in C. And recall the similarity to the definition of Kahn complexes. In Kahn complexes, we require exactly this, just for all I, not excluding 0 and n. And so typically you refer to, another way to refer to these is as inner Kahn complexes, right? Because we require inner horns, the ones with index between 0 and I, to be fillable. All right, that's already what an infinity category is. And a functor between two infinity categories is simply a map of simplicial sets. So that's surprisingly easy, but as of now it's not obvious what this has to do with categories. So I will explain that after cleaning the board. So to begin with, let's see how just ordinary categories are related to this. So as an example, if we start with an ordinary category C, then we define the nerve of C to be a simplicial set whose n simplices are simply given by the set of functors from n to C. Here, n is the poset of numbers from 0 to n, just the regarded as a category. So an n simplex is simply a diagram of objects C0 to Cn in C and a sequence of maps. And this is functorial in n, so it defines a simplicial set. Faces and so on are explicitly given in terms of dropping indices and forming composites. Sure, you've seen that or can work it out. And it turns out this actually defines an infinity category. So for this simplicial set, we have these inner horn fillers. Indeed, we have them uniquely. And furthermore, it turns out that functors between the nerve of, or maps, functors in this sense, so maps of simplicial sets between the nerve of one category and the nerve of another category simply correspond to functors of these categories. This is a really good exercise, so I'll give you some time to think about that and try to work it out yourself. So of course, if we form the nerve of a category, we can still recover its objects and morphisms simply as the 0 and 1 morphism, the 0 and 1 simplices. So inspired by this example, we will now define for a general infinity category that we will call C0 the set of objects, and C1 the set of morphisms. Note that it's not obvious at this point what composition of morphisms should be. As of now, this is just two sets we can define in terms of an infinity category. And note that if you have a one simplex, you can take its two boundaries, which give you two objects. So we will think of a one simplex F as a morphism between A and B, where A is the first vertex and B is the second vertex, right? Partial I denotes the boundary operator that drops the ith vertex. And note that in addition to these boundaries, we also have a degeneracy map from C0 to C1. You should think of this as assigning to each object the identity morphism at this object. There's one particular relation we have on morphisms, which is that we have two different morphisms with the same endpoints, then we call them equivalent if there exists a two simplex of the following form. Its faces are F, G, and the identity at B. Remember, that means just the degenerate one simplex at B. And yeah, it's a two simplex. So we will write this homotopic symbol, and it turns out that this is actually an equivalence relation on the set of morphisms with two given endpoints. Also note that in the example we have considered so far, in the nerve of a one category, this equivalence relation is actually discrete. If you have two different morphisms and they're equivalent, they're actually already equal. So far, we're somehow seeing exactly the data of a category here, at least in the example we've considered so far. So let's now move to a different example where this equivalence concept gives us something interesting. So if C is already a Kahn complex, then of course it's also an infinity category. Remember, we're requiring strictly less in the definition of an infinity category, namely only fillers for certain horns and not all of them. So in particular, for a topological space X, sing of X is an infinity category. And let's think for a second about what objects, morphisms, and this equivalence relation mean here. Here, objects are simply points of our topological space X. Morphisms are paths in X, and between their a path gives you a morphism between its endpoints, of course, and these identity morphisms are simply constant paths. And finally, this equivalence relation corresponds to homotopy of paths relative the endpoints. So in particular, if you would pass to equivalence classes of morphisms, then what you would see here is exactly the fundamental groupoid of X. And so you should think, in this world, you can think of Sing of X as some kind of infinity categorical version of the fundamental groupoid. So we will now have to discuss composition of morphisms, and this is where this behaves a little different from classical category theory, because as you see already here, composition of paths is a subtle operation, right? There's different ways to compose paths depending on how you choose to parameterize them, and no matter how you do that, you run into something that's not really associative, only associative up to homotopy. So let me explain that after cleaning the board. So let's make the following definition. For morphisms f from A to B, G from B to C in an infinity category, so just one simplices that agree at the suitable vertex, then a composition, notably not the composition, just a composition of F and G is a two-simplex sigma with A, B, and C as its vertices, and F and G as the one-simplices. And there's a third one-simplex, of course. Let's call that H here, right? It's just the third phase, the middle phase of this simplex. And in this situation, we will write H equivalent to G after F. And notice that somehow, so first of all, existence, whenever we start with G and F, existence of such a sigma is guaranteed by just the axioms of an infinity category, right? We just have to fill the 2-1 horn here. And it's a little weird that we're somehow not fixing a choice here. But it turns out you can check that the H you get out of this is still well defined up to this equivalence relation. So in other words, if you choose two different sigmas, you get equivalent H's. And so even though this maybe seems like a little kind of defect, we don't have a composition on the nose, so this sounds a little weird. Just think of the fact of ordinary category where, for example, coproducts are also not baked into the structure, right? The coproduct of two objects is only well defined up to canonical isomorphism. And that's good enough to work with. And it's even easier to work with than if you, say, endowed your category with the structure of a coproduct functor, because then you have to think about how associative is this and all that. So this is kind of a consequential way to extend this also to the structure of composition. And building on that, we will also define the notion of equivalences in an infinity category. So if f from A to B is a morphism, then we call f an equivalence if there exists a G in the opposite direction such that there are compositions like this, that somehow we can find two simplices that show us that the identity at A is this composite and the identity at B is this composite. This is very similar to what it means to be an isomorphism in an ordinary category, just that we have this kind of weak composition that's only well defined up to equivalence. So in terms of infinity categories, we can also talk about functor categories between them. So let C and D be just simplicial sets for a second. We'll see what happens if they're also infinity categories in a second, but for now they're just simplicial sets. And we define another simplicial set, which we write fun CD with n simplices given by the set of maps from C cross delta n to D. And you'll notice this is precisely the usual definition of the simplicial mapping space, right? For any two simplicial sets, I have a simplicial set of maps defined like this. But we're calling it functor category here because its zero simplices are simply functors if these are infinity categories. And it turns out, in fact, that under mild assumptions, this is again an infinity category. And I'm saying mild here because you need a little less than what you would think. You don't need that C and D are infinity categories. You just need that D is an infinity category. So, which shouldn't maybe surprise you because after all, you can do all these horn fillings and so on in the target, but of course the proof of this involves some non-trivial combinatorics. So if you think about what morphisms in this infinity category are, a morphism eta from F to G is a functor C cross delta 1 which restricts to F and G on C cross 0 and C cross 1. So we will call those natural transformations. And you can show, this is analogous to usual category theory, that being an equivalence in here, in this sense, so that you find an inverse natural transformation, is equivalent to being object-wise an equivalence. So what does this mean? This means that eta is an equivalence in this functor category if and only if eta c is an equivalence in D for all objects C in C. And eta c, of course, just means that if you take an object in C, then this map just gives you a single one simplex in D. We will now talk about equivalences between infinity categories. So a functor between two infinity categories, C and D, is called equivalence if there exists a functor G in the opposite direction and natural equivalences between f composed with G and the identity functor on D and G composed with F and the identity functor on C. So if there is an equivalence between C and D, we will call them equivalent and sometimes simply write C equivalent D. So from ordinary category, you might be familiar with the very useful characterization of equivalences in terms of being essentially surjective and fully faithful, which is typically much easier to check than explicitly writing down an inverse and natural transformations like this. And we will now want to develop the same kind of characterization in our world of infinity categories. However, as of now, we don't really have, we first have to talk about a concept of mapping spaces in order to make that precise. So for objects A, B in an infinity category C, we define a simplicial set map in C from A to B as the following pullback. Here we're putting fun delta 1C, right, the simplicial mapping space from delta 1 into C. And down here we have two maps of simplicial sets from this guy to C, given by restricting to the first vertex or the other vertex. This gives us a map down to the product C cross C. And in that product, we have a point simply given by the objects A and B. And this mapping space from A to B is defined as the pullback of simplicial sets here. In fact, this is also true, but not that easy to prove. This is actually a Kahn complex whenever C is an infinity category. And something you can directly see from this, though, is that the zero simplices in here are precisely morphisms in C with endpoints A and B. So morphisms from A to B. And we have a one simplex between any two morphisms from A to B, if and only if they're equivalent. So that uses a little bit. That uses basically what goes into the fact that equivalence between morphisms is an equivalence relation. Same style of argument. But what this means is that this is a Kahn complex whose pi 0 is simply the set of equivalence classes of morphisms A to B. Right, so this is a sensible kind of mapping space. So in terms of these mapping spaces, we now call a functor f from C to D fully faithful if the induced maps from the mapping spaces in C for any pair of objects to the mapping spaces in D for any pair of objects are homotopy equivalences of Kahn complexes. So maybe one has to think a little bit for a second why this is natural, but obvious from the definition basically. And now note that this does imply that you get bijections on sets of equivalence classes of morphisms, but we're requiring much, much more here, right? We're not requiring that this is an isomorphism on pi 0 only, but basically also on all higher homotopy groups. So this is not something that you can easily check just on morphisms as we talked about them so far. This is somehow a much stronger condition. Compared to that, the definition of fully faithful is much more like you would expect. Of essentially surjective is much more like you would expect, right? A functor from C to D is essentially surjective if for every D in D we find a C in C and an equivalence between D and f of C. Right, so this is something that's just phrased in terms of equivalence classes of objects. And now in terms of these two definitions, we do in fact get the result that that you would hope for coming from usual categories, namely that a functor C to D is an equivalence of infinity categories in the sense that there is a functor in the other direction and natural equivalences, if and only if f is fully faithful and essentially surjective. And this is hard to prove, but kind of a foundational result about infinity categories. So another thing that we can kind of pull over from usual category theory now is the notion of the full subcategory on a set of objects. So let S in C0 be some subset of objects, then we define CS as the following simplicial subset, CS in C consists of all simplices with vertices in S, and you can directly from the definitions check that this is indeed an infinity category. Basically, all the diagrams you need to consider, like somehow you get a horn filler in here and that automatically lives in here again. And also note here that somehow if we do a variant of this construction and we first pass or we first saturate S under equivalence of objects, i.e. we form a larger subset of objects consisting of all objects of C which are equivalent to objects in S, then we get a functor from the full subcategory on S to the full subcategory on S bar, right? Simply the inclusion. And now this is obviously fully faithful and essentially surjective. Essentially surjective is clear, and fully faithful is basically because the pullbacks that define mapping spaces, if you write it out, you see it's just the same simplicial set. And so from this result up here, this is an equivalence. So if you're interested up to equivalence of categories, then this is a move you can always do without changing things. We have previously seen composition of morphisms, just of two individual morphisms. We have now seen that somehow we don't just have morphisms, we really have these mapping spaces. So we will now revisit the notion of composition and see that it really gives us maps between mapping spaces. So to do that, let's pick three objects, A, B, C, in an infinity category. And now we define some kind of triple mapping space. Map C, A, B, C, where here we take the mapping space from the 2 simplex into C. Here we take the map that comes from restricting to the 3 vertices. And down here, we take the map that comes from the 3 given objects, A, B, C. And again, we form this kind of pullback. So if you recall how we defined composition of morphisms, where we said that a composition of G and F is given by a single 2 simplex, then you might see where this is going. Here we're setting up a space of 2 simplices in C which sits at the 3 given objects. And so in fact, there's the following lemma. This guy is Khan, and we have the following diagram where we have this space of 2 simplices at the vertices A, B, C in the middle, and then we can restrict along somehow the middle face of our 2 simplex to get a map into the mapping space from A to C as defined previously, but we can also restrict to the other two faces to get a map back to map BC cross map AB. And it turns out this map is a homotopy equivalence of Kant complexes. So this diagram is induced by this diagram, where here you include the inner horn and the other face. And so you should think of this fact that this restriction map is an equivalence, this is restriction to this inner horn, as some kind of version of the horn filling property in families somehow. So the proof again is a little bit technical, but basically it follows somehow from the horn filling property in C. And so again, we're somehow in the same situation as when we defined composition of two individual morphisms, where we said, given two morphisms, we can pick a composition. There are multiple ways to do so. And then we can look at the final, like the middle face of the chosen composition and say that is somehow a composition of our, or the composition up to equivalence of our two morphisms. And you see, this being a homotopy equivalence really allows you to invert this map just uniquely up to homotopy. So a choice of a homotopy inverse S fits in through the following composition, right? We can go from the left guy along S to this kind of space of chosen compositions, and then we can further restrict like this. And we can call this map composition, and for the moment let's index it by S, because somehow we've made a choice here. But as it turns out, given a map, you find a unique homotopy, given a homotopy equivalence, there's always a unique homotopy inverse up to homotopy. So any two different choices of S here give homotopic composition maps. So that's a common theme in infinity categories, that sometimes you have to make choices, but if the definitions are chosen well, then you can reduce somehow to choices being contractible. So in fact, the space of all homotopy inverses to this map you can show is contractible. This is a stronger version of saying that any two homotopy inverses are homotopic. And so this composition map is really unique in a suitable way. There's just not one preferred choice for it. And similarly, in this language, one can think of associativity as somehow there also being a space of kind of chosen composition data for 4 vertices, and then this somehow parametrizes associativity of this composition map. And a nice thing to look into, or a nice thing to compare this to, what's going on here, is so-called Segal categories, where somehow you make spaces like this part of the data to define sort of categories weakly enriched in spaces. The upshot is that we get something like that for free out of just the datum of an infinity category, of our single simplicial set C. So one thing that people often say is that this data somehow defines an enrichment in Kahn complexes up to some kind of coherent homotopy, right? There's no choice of this composition, of these composition maps, where this is strictly associative, at least a priori not. So as a good exercise for this section, it is you should examine all the things we did in these examples. So in particular, in the example of the nerve of a one category, you can see that all of the things we defined sort of are just generalizations of the usual notion. If you apply them to the nerve of an infinity category, of a one category, you'll see that they specialize to the usual version of these definitions. In particular, you can check that the mapping spaces in the nerve of a one category are really discrete. And the composition map here is really ordinary composition. And it's also nice to examine what this map is exactly for the example of Sing of a topological space. Up until now, we have seen two kind of very different examples for infinity categories. We've seen ordinary one categories, which somehow live inside this theory, but in a somehow trivial way. All the mapping spaces are discrete and so on. So this doesn't give more than just the usual theory of one categories. And on the other hand, we've seen that Kahn complexes give infinity categories. In fact, ones where all the morphisms are invertible, so you could call those infinity groupoids. We will now see an example which is somehow of a different flavor, with interesting mapping spaces and non-invertible morphisms, and that's the infinity category of spaces. For us, spaces always means Kahn complexes here. So the objects will be Kahn complexes, the morphisms will be maps of Kahn complexes, and then somehow equivalence of morphisms will correspond to homotopy, and you'll somehow see a lot of the homotopy theory in the mapping spaces and so on. This is somehow the foundation, like the fundamental example of an infinity category, very similar to how set is the fundamental example of a category. For example, just as categories are enriched over sets, right? The set, every category comes with sets of morphisms. We've seen that every infinity category has mapping spaces which land in Kahn complexes. So in some sense, they're also enriched over Kahn complexes, or over the infinity category of spaces. So to define an infinity category with Kahn complexes as objects, we first recall that we can define a category of Kahn complexes which is enriched in simplicial sets. Right? Simply by having objects being Kant complexes and the enrichment given by simplicial mapping spaces. And in fact, in this example, one can check that the mapping space between two Kant complexes is again a Kant complex. So this is really the enrichment lands in Kant complexes. So how do we turn that into an actual infinity category where somehow we have built these mapping spaces in? Well, here's a construction. So if J is any finite, non-empty, totally ordered set, then we will define a simplicity enriched category C of delta J, which has objects simply given by the element of J, and then a simplicial set of maps from I to J for any elements I and J of J, simply as the nerve of the following partially ordered set consists of all subsets of J where the minimum of my subset is I and the maximum of my subset is J. And if you think about it, so if we identify J with just the set of numbers from 0 to n for some n, then what is this poset? Well, it consists of all the subsets that land in that lie in the interval between I and J and do contain both the endpoints. So as a poset, you can work out that this really looks like a cube of dimension J minus I minus 1. Simply somehow where the coordinates of the cube index for each element strictly between I and J, whether it's in or not. So the nerve of this is really a simplicial cube. This is maybe another good exercise. And the composition of morphisms in here is induced by union of the case. So this is functorial in J, obviously. So this defines some kind of co-simplicial object. And also, if we look at this carefully, what have we achieved here? Well, we've defined a category with objects J and simplicial mapping spaces, which are all contractible, right? They're all cubes, so they're weakly contractible. So you should think of this as some kind of blown up version of just the ordinary category you can get out of J with objects, elements, and morphisms, points, right? So similar to how we defined the nerve of a one category previously, we can now use these kind of blown up versions of totally ordered poset categories to define some kind of fancy version of nerves, of simplicial simplicity enriched categories. So let's just do that for this simplicity enriched category for now to see it in action. So we define a simplicial set, curly S, by saying that n simplices are given by the set of functors of simplically enriched categories. So that's functors compatible with the enrichment. So let me put a little simplicial set up here to indicate that. From this thing, where now our ordered set is really the usual 0 to n, into the simplically enriched category Can. So what have we got here? Well, 0 simplices. What's going on there? Well, C of delta 0 is just a category with one element, with one object, and no non-trivial morphisms. So this is really, these functors here are really just giving us objects of Can. So 0 simplices are Can complexes. Similarly, 1 simplices, well, in the case of delta 1, this is really just two objects and morphisms from 0 to 1 given by a point. So in that case, it just recovers ordinary morphisms in here. So here we get maps of Can complexes. And now, here's the first interesting thing that happens, and that's really worth working out explicitly in terms of, well, checking what happens for delta 2 here. So a 2 simplex in here consists of 3 objects, x0, x1, x2, and maps f2, f0, f1 like this, plus a homotopy between f1 and this composition. And now it turns out, and again this is not easy to prove, that this S is in fact an infinity category, and for any Can complexes x and y, we have an equivalence between the mapping space in that infinity category and the just simplicial mapping space. So Hom in the simplically enriched category Can from x to y. Right? This is a homotopy equivalence of Can complexes. So we see that somehow up to equivalence, this really gives us an infinity category with the mapping spaces we wanted to build in. And in fact, one can argue that these are compatible with composition in a certain way and so on. So this is originally due to Joyal. And we can say what's going on here a little bit more generally, namely for an arbitrary simplically enriched category C, we can define the simplicial or homotopy coherent nerve of C as a simplicial set, like we did for Kahn complexes just here. So simplically enriched functors of these C of delta n into our category. And then it turns out that this is if C is enriched in Kahn complexes, then this nerve of C is an infinity category, and we have equivalences between the mapping spaces in this infinity category and just the simplicial Hom in our simplically enriched category. So this is one of the most important sources for examples of infinity categories, because in many cases you do have some notion of objects with spaces of maps between them, and then you can take this kind of nerve to end up in the world of infinity categories. All right, thanks for watching. So this concludes our first video on infinity categories. There will be more about colimits and then stable infinity categories next. Note that somehow we gave a very rough overview and omitted basically all the proofs, some of which are very technical and very difficult. So I encourage you to check one of the many good books on the topic for more details.